I just want to introduce our next speaker, Dr. Ofer Naaman. He's a research scientist with Dual Quantum AI, where he leads the readout hardware team. He holds a BSc degree from Tel Aviv University and a PhD from UC San Diego. Before he was at Google, Ofer was at NIST Boulder, UC Berkeley, and Northrop Grumman, where he worked on a variety of different topics ranging from single electron transistors, quantum computing, and parametric amps, to superconducting logic and project memory. So without further ado, let's welcome our next speaker.
All right, thank you. I hope people can hear online. If not, please yell and we'll help you help me set it up. So yeah, I'm Ofer Naaman. I'm from Google. I'm going to be talking about frequency domain simulation of superconducting circuits. In particular, I'm going to talk about how making our simulation tools be aware of flux quantization and the constraints that they bring in superconducting circuit. So this is work that we've done with Keysight in collaboration with Keysight. So what I'm going to show you is going to be based on Keysight ADS, which is a EDA software. I'm hoping to give you enough detail about implementation so that you can take what I'm showing you and implement it in your favorite simulation software, whether it's AWR or Cadence or some open source like LT-Spice or QX or whatever you like to work with. So I'm going to try to give you enough detail so that you can do that yourself. Okay. So flux quantization. So what does that mean? That means that in a superconducting circuit, any loop or any closed superconducting piece is going to be enclosing a magnetic flux that is an integer multiple of the flux quantum, and the flux quantum is this quantity here. So if I have a superconducting ring, I can have either zero flux inside or a flux that is any integer multiple of phi naught. Okay. The reason that this happens is because the superconducting condensate is in fact represented by a single quantum mechanical wave function that has to be continuous. Therefore, if you have a ring, it has to be 2 pi periodic. The gradient of that superconducting wave function, or the gradient of the phase, is going to correspond to a vector potential, and that is basically a magnetic field over this surface. And that, again, because of periodicity, has to be integer number of this phi naught quantity. All right, so this was a cartoon of a superconducting circuit. We can represent it as a schematically as well. The superconducting wire that carries the current, we're going to call that an inductor, and that inductor is going to be associated with some flux as well, because there's current flowing through it. And we actually can apply magnetic field bias into, or flux bias into this loop through, say, a mutual inductor or some transformer. Okay? So this is what the circuit looks like. So again, the current in the inductor, in a superconducting inductor, is associated with the flux. We can bias it with external flux by passing current through this transformer, through the primary of this transformer. And the voltage, as usual, is the derivative of the flux, for example, at this node. Okay, and again, we have flux quantization. So the sum of all the fluxes from the inductance, from the external flux, has to be adding up to an integer multiple of phi naught. And so when you're looking at this circuit, you already see that you might have a problem if you're going to try to simulate it with a solver. Because the DC, I can put some flux bias, there'll be a DC current flowing through. It's DC, so the voltage is going to be 0. Because the impedance of these inductors at DC is 0, then really you can have any current in the loop satisfy that condition that the voltage is 0. Okay? So circuit simulator will attempt to solve this. It can choose whatever it wants, and it will. Okay? So we have to try to tell the simulator how to think about flux quantization. So in other words, like in the simulation world, what the circuit simulator does is solve for voltages and currents. Okay. Whereas in the superconducting world, we really want to care about the flux and the charge. Okay. Now these are both integral. So when we're solving this, we're dropping integration constants, and those integration constants are important because they put additional constraints on the solution. So yeah, so we need to take care of these constants, and so in superconducting loops, the things that we care about is flux quantization, and in fact, it matters for inductances that are not gigantic. Okay, so if your inductance is less than 300 nanohenry, you probably should care about flux quantization. The other constant that we drop is the charge quantization. So charge comes in packets of electrons, and this becomes important if there are superconducting islands. But you can see that if the capacitance is bigger than about a femtofarad, the capacitance of the island is bigger than about femtofarad, you maybe don't have to worry about it that much. So what we're going to do is we're going to be, for our purposes, where we're working with microwave circuits that are usually low impedance, meaning the inductance is not that large and the capacitance is not that small, we're going to be safely ignoring charge quantization, but we really cannot ignore flux quantization. So that's what we're going to chase now. So how do you make a circuit solver understand flux quantization? So if we're looking at a loop of superconducting devices, maybe some inductors, maybe some Josephson junctions, we can write the condition about flux quantization. It's basically the sum of all the phases of all the junctions, the sum of all the fluxes on all the inductors. That has to equal the externally applied flux plus some integer constant. Okay. If we're looking at that equation, this is basically a scalar equation, which looks a lot like Kirchhoff law for the voltages. So if we can represent all the phases as some fictitious voltages, we can just tell the circuit simulator, okay, well, these are voltages, just do your thing, and it will come up with a solution that satisfies that scalar equation. So that's what we're going to do. So we're going to express all the voltages, all the fluxes as voltages, either for the junction, we're just going to take the phase divided by 2 pi, or the flux in the inductor, and we're going to map it so that like 2 pi phase is going to, or phi naught is going to be 1 volt. And then we basically going to have to build an auxiliary circuit that is going to be solving this equation for us, for all the fluxes. So just to recap, we're going to have an electrical circuit. So this is like illustrated here in the green. That is going to be dealing with real currents and real voltages that we're simulating. But we're going to have another coupled circuit, which is shown here as red, which is going to be an auxiliary circuit that makes sure that whatever we do in the electrical side, we're going to be satisfying the condition that all the fluxes have to add up to an integer phi naught. Okay, so in order to, let me go back. In order to do that, we need to have new components. We need to have definitely junctions, but these junctions going to need to have some terminals that express the phase across the junction as some voltage. And we're going to have to do that also with inductors. So we're going to have to take an inductor and make a component that has the inductor plus two more terminals that express the phase or the flux across that inductor in terms of a voltage. And then we can build that circuit. All right, so let's talk about how to build a junction. So we're going to make a model for a Josephson junction. A Josephson junction basically is described by these two differential equations. The first equation is basically saying the voltage is the time derivative of the flux, or the phase in that case. That is what the first one's saying. The second equation is relating the current through the junction to three different parts. One of them is just the resistive current through some shunt resistor. The other one is some current through a capacitor that's shunting the junction. And the important part is this Josephson term, which said the current is proportional to the phase across the junction. Okay, so these are the usual equations for the Josephson junction. Let's implement them as a circuit. Okay, so what do we have here? Let's look at these two terminals. These are the terminals of the Josephson junction. There'll be some voltage across them. That's the voltage across the junction. We can implement these two terms in the second equation very easily by just using this linear shunt components, the resistor and the capacitor. That's not a problem. The next thing we need to do is we need to integrate the voltage to get the phase. So how do we do that? We actually use a trick from this paper. And what we're going to do here is we're going to take the voltage, we're going to convert the voltage to a current with 1-to-1 magnitude. So basically, we're taking the numerical value of the voltage, just expressing it as a current on this side. We're letting that current charge up a capacitor that its value is phi naught, so that we get all the constants right. And basically, that in the simulator, that will perform this integral. Okay, a capacitor is an integrator. So the voltage that appears across that capacitor is going to be the time integral of the voltage at the junction terminals divided by phi naught, which is exactly what we want. Okay, so we have the electrical part of the circuit here. We have the flux part of the circuit here. We can output the flux voltage between this node and that node on external pins. And the last thing we need to do is to express this first part of the equation. So we're going to have a device that measures the voltage on this terminal, which is essentially the flux, multiplies it by 2 pi, take the sine of it, and multiply it by a constant. Okay, and that will be the current at the second terminal, and that current is essentially fed back to the terminals of the junction. Okay. So this is how we implement Josephson junction with really basic elements that are available in most simulators. Okay, so yeah. All right. If you're using ADS, so ADS 2025 actually provides a number of behavioral models that implement those equations directly. So I think they're written in Verilog A or something like that. But they're making a few devices available to you. You have just the two-terminal junction. Basically, the phase is internal to it. You can have a three-terminal junction that has the electrical part and has one phase node that is assuming that is basically zero reference, give you the voltage proportional to the phase. And you have the fully differential JJ4 component that basically give you the differential phase as a floating voltage. So the first two are available in the regular library. The second two, you need the Quantum Pro package. Right. So now you can in fact build you can build the four terminal one. You can build from a 3-terminal junction just by adding a transformer and doing the single-ended to differential transition. Okay. So we talked about the junction. We need inductors too, and we're going to use very similar trick to what we did with the junction. Again, if you're using ADS, these are devices that are provided to you in the library. If you don't use ADS or you don't have access to this package, what you can do is you can do a very similar trick, take the voltage across the inductor, convert it to current, integrate it on this capacitor. And then once you have that, you can just calculate what is the current, because you know that the current is going to be pi naught over L times the voltage or times the phase at the input. Okay, so this is how you make an inductor, very similar to how you made the junction. So now we have yeah, you can extend that also to a mutual inductor. Now you have two coils, each of them has a phase drop and they are mutually coupled, so current through L2 will put phase on L1 and vice versa. So the way that you do it is you do the same trick, but now instead of a 2x2 matrix, you have a 4x4 matrix, and basically your matrix is solving this equation that relates the currents to the phases. Okay, so you can use just a linear Y matrix to do the calculation for you. Okay, anyway, so far, flux quantization is important. We have to care about it. It's a key constraint on superconducting circuits. The usual standard frequency domain circuit simulators don't know anything about flux quantization, so we have to help them. We can do that by expressing the flux using voltages on an auxiliary circuit that has to satisfy Kirchhoff law. And we need special components that we can build, like inductors, mutuals, and Josephson junctions. These are available in ADS, but I showed you how to build them, so you can build them in any software that you like. So let's go into some examples. So I want to show you a few simple circuits that use that methodology and show you that they actually work. So the first one is SQUID. This simple circuit that has one junction, one inductor. We can couple flux into that loop. We can calculate what is the equilibrium phase of that by writing the energy, minimizing it, finding what the phase versus flux equation looks like. We are going to work with ratio of the junction inductance to the linear inductor such that there's only one solution, so we're not talking about multi-well potentials. And we can build a circuit. So this is what the circuit looks like in ADS. We have the outer loop is the electrical loop, so it has the junction, it has the inductor with the transformer, and then the inner loop expresses the flux or the phase relations in the circuit. And as you can see, basically you can write down the equation and just connect the dots with correct polarity. We're going to be measuring the phase across the junction at this node, and we're going to be looking at the current in the circuit over here. And we're going to do that versus external flux. And if you know what the phase versus flux relation of a SQUID looks like, this will be very familiar to you. We can sweep the ratio of the linear and Josephson inductance and see that as we get closer to beta L of 1, this curve becomes sharper, as it should. And we can look at the current versus external flux, and it looks very non-sinusoidal, as it should. So this all can be calculated analytically, and we can compare it, and it agrees with the simulation. The second device is also an SQUID, but now I split the inductor in two parts, and they're both going to ground. And what this does is make this a tunable coupler. So there will be some flux where the inductance of this junction diverges when the phase of that junction gets to pi over 2. That means that there will be no coupling between these two ports. So there's a port here and the port here. If that inductance is infinite, there's no coupling between them. Again, we can express we can write down, the flux quantization condition and connect the dots with the correct polarity. Here we can introduce flux bias directly as a voltage source on the flux loop. So that's another useful trick. And we're going to do an S parameter simulation, basically looking at the transmission from port 1 to port 2, and plot that versus flux in the loop for different values of beta. So you can see that there's a point in flux that the transmission goes to 0. That's the point where the coupler is off. And we see that that point changes with the value of beta L. And also you can see that when beta L equals 1, the transmission exactly at phi naught over 2 is unity. So this all agrees with what we understand this couplers to do. All right, so so these were two examples. Before I go to the more complicated examples, I want to say maybe a few words about why we, in fact, went that way and started this project. Is because we need to design devices for readout. And for that, we need to understand better what we're doing, so we want to simulate stuff. So readout really, in a nutshell, we're going to send a signal to our qubits. It's going to jump back at us. It's going to have a phase shift on the signal that associated with this with the state of the qubit. This is kind of like binary phase shift keying. If you like to think about it in communication language, we're going to have as the result that we're going to get is going to be a dot either here or here. If we can associate the dot with this blob, we're going to say the qubit was at state 1. If the dot can be associated with this blob, we're going to say it was 0. So this is kind of what the readout looks like. We're going to need to have less than 1% error. The time that we have to integrate is about 200 nanoseconds. And we have very, very low power. That means we're going to have very, very low noise receiver chain. We cannot use the regular LNAs by themselves because they have too much noise. So we need to build parametric amplifiers. Okay, we need to get 20 dB of gain with essentially quantum limit noise performance. This stuff is big, so it takes a lot of room on our fridges. Therefore, we need to multiplex. So we need to read multiple qubits with each of these receiver chains. To do that, we need to make the paramps and the whole receiver chain broadband, and we need high dynamic range as well. Just a little bit about how parametric amplifiers work. Essentially, we're going to take an reactance in the circuit and start modulating it, and we're going to modulate it at twice the frequency of the resonance. What that does effectively is changing the inductance in a circuit can do work on the circuit. Essentially, changing the inductance under constant current is doing the work. So you can see in this movie that if you make the potential shallower when the ball has to climb up the side, and then you sharpen it so it's sharp when the ball rolls down, you can actually pump energy into the circuit. So this is kind of how it works. In the superconducting world, we have to actually implement a tunable inductor to do that. So there's multiple circuit topologies. I think they're pretty exhaustive. You can implement it as a T-circuit. Basically, you have a junction or a SQUID to ground, and you can pump flux through it. This looks like essentially a T transformer. And you can do it with sort of a tunable coupler kind of architecture where you have really a pi circuit here. Again, you can change the value of the inductance with flux, or you can do it as a balanced bridge. There's pros and cons to each of these arrangements. But anyway, this is kind of how you build parametric couplers.
Question online. Given the duality condition between processing function and quantum phase shift junction,
yes,
how would you approach creating a quantum phase shift junction component using a similar technique?
I haven't thought about it. It's a good question. There's a number of devices that could be used for, well, that I would like to have models for. So that includes phase slip junctions, hotspot devices like Entrons and stuff like that. So yes, definitely, there's a lot of more to do there. Okay, so let's go back to examples. So this is actually an example from a paper from the Yale group. The nonlinear device here is a SNAIL array. So a SNAIL is kind of like a SQUID, but it has one small junction on one side and 3 big junctions on the other side. Kind of looks like an R SQUID, but the inductance here is nonlinear, which is help. An important quality of the device is that there will be some flux bias where we can minimize unwanted nonlinearity, so fourth order nonlinearities in the system. So we'll have a pure three-wave mixing, no four-wave mixing terms. That makes the device higher, basically support higher saturation. So what they did is they took this device, made the chain of it like 20 long and stuck it in the middle of a transmission line. They were pumping the transmission line from one side and the signal comes in from the other side. This makes a parametric amplifier. You can do the simulation, tune the gain at each flux bias to say 20 dB. Tune the pump frequency and amplitude so that you get 20 dB gain. And then you can look at two things. You can look at what is the saturation power at that flux bias point, and you can look at what are the intermodulation products at that point that will tell you about the nonlinearity. And what you can see is that the saturation power, which is shown here in orange, indeed has a maximum at a particular flux bias. At the same time, you have a minimum in the intermodulation product, so basically mixing terms of two tones. And that indicates to you that this flux, you essentially minimize the fourth order nonlinearity. So this is what is called the curve-free bias, and the value of that bias matches the results in the paper. Okay. Yeah. Yes. Oops, that was 2 slides. Yeah, it's gonna run now until this is done. Yes. Here. Yes. So this is harmonic balance simulation. Absolutely. So yeah. So this is a 2-tone source, and we're using harmonic balance simulator in ADS to do this simulation for sure. Okay. Cool. The other device that I want to show you is a device from our group. This is essentially a multipole lumped element parametric amplifier. It's designed to be to have a gain profile of 3-pole Chebyshev. Prototype, we're going to have 20 dB of gain, 1 dB ripple, about half a gigahertz bandwidth, and we design it for high saturation power. Negative 95 dBm input saturation. This is kind of what the design look like. This is the schematic. I want to focus on that nonlinear element, which we call the snake. Oh yeah, we measured that. It kind of works. Anyway, the snake. So the snake is basically an array of interleaved R SQUIDs. This is what it looks like in reality, and if you zoom in, this is what the left looks like. So there's basically a bunch of superconducting loops with junctions. There's a big bias transformer here, and we want to understand how this works. You can build yourself a unit cell of this array. Again, we're going to use flux quantizing components. So there's junctions with the phase terminals. There's inductors with the phase terminals. You kind of have to be careful that you're putting everything with the correct sign. But if you're careful, this will work. Basically, we have two coupled circuits here. We have the electrical circuit in black. We have the phase or flux circuit in blue. We're going to constrain the flux in each of these loops to be quantized. And also because this large array connecting in the end over itself, we're going to have to do flux, essentially constrain the flux over the whole array as well. So this is kind of what the unit cell looks like. You can then build a larger circuit by cascading those unit cells, connecting them. There's another inductor here as well. We have the bias transformer is here, so this is usually the mutual inductance cells. And you basically build this whole thing, you connect it to your simulation, you can say, okay, what is the inductance of this as a function of flux? So you can measure the S11, convert it to impedance, and then from that extract the inductance. The simulation here is in blue. Some cheesy numerics is in orange here. We see that there's pretty good agreement. I tend to believe ADS more than the numerics because the numerics were the analytic solution make assumption about this array being infinitely long and uniform, which is not. So great, we know the inductance versus flux, so we can bias it at some point and modulate the flux. That will give us the parametric action. So we do that. Here's this snake array. We can pump it, shunt it with the capacitor, connect it to a bunch of microwave elements, and do harmonic bias simulation to see if we got any gain. And in fact, we do get gain, and it looks quite similar to what we designed and to what we measured. And also, you can increase the input power and see where the gain compresses, and that again gives us a result that is very similar to what we measured in the lab. Okay, so I gave you a few examples from designing devices. I kind of want to talk a little bit about how we can use simulation to sort of explore new devices. I will not get into a lot of details here, but essentially, when you're talking about parametric amplifiers, you can think about the circuit as seeing a negative resistance or a negative damping. That's where the amplification comes from. So you have a circuit basically which includes a resonator with some negative damping. It's coupled to its environment with some rate for a matching network. That is the dissipation rate. And now to get gain, you want the conversion rate to get close to the dissipation rate, but not exceed it. If you're exceeding it, then you're going to have runaway oscillations or self-oscillation. So to get high gain, you want to be just, the conversion rate has to be just right under the dissipation rate, okay? But cool, so we have like a negative resistance. We can think about this negative Q or an anti-damping kind of parameter. We understand how to set that value so that we can get gain that we want. And the question is, does that give us does a circuit, a nonlinear circuit like a SQUID or a SQUID array, does it have any limitations on how much gain we can get or how much bandwidth we can get? So you work through the circuit design and you find out that the gain that for different gains you have you can plot a curve of the fractional bandwidth product with the anti-damping dissipation or anti-damping Q factor. Okay, and you can do that for different matching network designs with different gains and different ripples. You can also express the anti-damping as a ratio of the linear inductance in the circuit to the magnitude of the modulation. So if you modulate the inductance with a higher amplitude, you're going to get lower Q, which means you can match it with a wider bandwidth for a particular gain. You can also relate that quantity to things that you can measure in simulation. So if I connect my nonlinear device here and I'm exciting it, and I'm looking at the conversion process, so S21 will be the conversion, I can essentially measure what this anti-damping Q directly from this electrical simulation. So for the snake device that I showed you before, you can do the simulation, say, look at that anti-damping quality factor as a function of flux bias as in a function of pump amplitude. And we can see that the damping, like it doesn't really matter. The damping, the maximum anti-damping you can get is always gets you to a Q of about 2. That was a surprise to me, okay? I knew there was a limit, but I didn't know that it would be, I thought you could get to lower Q. And it turns out that you can. I've tried to do it with the SNAIL device. Again, for a SNAIL that is operates in a stable regime, you again are limited to about Q of 2. So the question is like, okay, is that fundamental? Is that depends on the design of the actual SQUID? I think there's quite an interesting opportunity to look at what we can do to lower the anti-damping Q, because if we can make more broadband amplifiers. Okay. So far I've talked about nonlinear simulation with actual device models. And I want to show you in the last few minutes that that is not always necessary, because sometimes we want to model just the microwave circuit, maybe just the the small signal limit of these circuits. What we can do in this case is we can understand parametric interactions as really as an electrical circuit. What the circuit looks like is you can write the input in the impedance matrix of that nonlinear element when it's pumped, and you can linearize it, and you can find out that it basically looks like an inductor sandwiching this ABCD matrix that looks a lot like what is called impedance inverter in microwave language. But it's basically purely off-diagonal ABCD matrix. If you understand that, then you can simulate your parametric amplifier circuit using this ABCD matrix as connecting between a signal circuit and an idler circuit. You can calculate what this value has to be because you know how the gain, the gain, and you know all the prototype coefficients for your design. So you can build a signal circuit with regular elements that are available in your simulator, whether it's ADS or something else. You can use ABCD matrix to simulate the linearized action of the paramp, but then you need to build a circuit to represent the idler, and these all these elements are just linear elements, but they're evaluated at the idler frequency. So they're evaluated at a different frequency than the simulation frequency. And you can do that by building yourself a library of I call them idler components. So they're just a capacitor, for example. You can simulate as a Y matrix that is evaluated at a frequency that is translated from the input frequency or from the simulation frequency. So you can do that for a capacitor, for inductor, for transmission line, any linear element that you want. You can actually write down frequency translated to the correct frequency. So that's basically brings me to my conclusion. Again, I want to emphasize that this work was done with Keysight. When we started this work, ADS 2024 had 2 elements in its quantum library. Now ADS 2025 has a much richer quantum device library, a number of SQUID, SNAILs, multiple junction models. So give it a try. We made Keysight ADS understand flux quantization. We can simulate flux quantizing superconducting circuit, and that is, really useful for more complicated circuit than just ones that have like 1 or 2 junctions. When you want to simulate stuff like a SNAIL array or one of our parametric amplifiers, you really want to have the simulator do it for you. You don't want to do like a lot of math all the time, right? So we built models, inductors, mutual inductors, junctions that have flux ports on them. I showed you how to do that. You can do that in any simulator that you want. I showed you a bunch of examples. And again, this has been very useful for us to understand our devices, being able to design them and to ask questions about the nonlinearity, for example. Yes, so that's it, I think. So thank you very much for your attention. I'll take some questions.
Slide 21.
Yes. Slide 20. Yes, I know. Here we go. Yes.
What is the distance between the ground plane holes and
So the question is the distance between ground plane holes and meanders. So which ground plane holes? These are not holes. No. So actually, this is a multi-layer process. So these are just fill shapes to get the edge to not being too dependent on our design.
there's no ground plane?
So there's no ground. The hole that you see is here. So there's a hole around this just because you want that mutual inductance to be large. So you remove the ground plane underneath. Yes.
Are there any highlights on what to pay attention to for kinetic inductance parametric amplifiers without phases?
Ooh. So should I repeat the question? Yeah. So if we are designing parametric amplifiers without junctions, where we're using the kinetic inductance to give us the nonlinearity, and not the junctions themselves, are there any things that I would be worried about or should pay attention to when designing this? I think for the particular problem that I was trying to solve here, it becomes important when you have loops. If you don't have loops in your circuit and you're quite confident about the values of your kinetic inductance, and you can model that in EM simulation or whatever, then I think this probably doesn't need to include this type of simulations that I described here. You should still have a model for what kinetic inductance looks like in your circuit simulation, and be able to simulate that accurately in harmonic balance, for example, to figure out, do you have intermodulation or saturation, and some, the stuff shift on you when you turn up the power and stuff like that.
I'm moving on the conclusion slide. You mentioned that the technique could also be implemented in other platforms like AWR or Sonic.
Yes.
I was wondering if you could elaborate more. For example, I'm not sure if this is a Keysight ADS is but AWR recently had access to AWR almost for free.
Yes.
So how much will go into producing in AWR?
Yeah, so the question was about translating this stuff to other platforms like AWR, because maybe your university has that, not ADS. The components that we've used are just linear components that you have in your simulator for sure, and controlled sources, which your simulator probably have for sure as well. And the only thing that you need to add to that then is a symbolically defined nonlinear device or a Y matrix. So I haven't played with AWR for a while, but I kind of looked through the manual, and they definitely have equation-based devices. LT-SPICE has equation-based defined voltage sources, I think. So you write the voltage equals and you write the equation and all that. And those come in like 1-port and 2-port versions. So if you have, you just have to read the manual, figure out how to use those things. But you can basically implement all that I showed with voltage control or control sources, and equation-based devices. And that's all we need.
The trade-off between a tupa and the broadband JPA, does it mostly come down to the resulting noise figure? That matter trading off the bandwidth of tupa to have a better noise figure in an operational band, which is really fast.
Yes, so the question was about tupa and how does tupa, what are the trades between tupa and JPAs essentially? So our readout band is limited to something between 500 megahertz to a gigahertz, not necessarily because of our amplifiers, but because of other constraints as well. So if we have a tupa that has 4 gigahertz of bandwidth, it's nice, but most of that bandwidth is not utilized. So we're paying a lot for that bandwidth. We're paying a much higher complexity. So we need like 3,000 junctions, bigger chip. We're paying a little bit in performance, although that is being worked on currently and being solved by a number of groups. So to me, it comes down to complexity. And I think, JPAs will take us, they have good performance in terms of noise. They're rather simple to build. We can understand a lot about them just from microwave engineering point of view. And we really don't need that much more bandwidth. So to me, that means it's a good trade. Now, if there's a reason for me to use more bandwidth, or I can find a way to simplify tupa design, and I can get essentially I can learn how to make them lower noise, then sure, I will use a tupa. I think it's mostly a kind of like a system level question about what you need versus what you can make.
Yeah, last week. Would the flux quantization approach discuss the programmable and Verilog file? In addition to this, how does this differ to WR Spice, where it is defined in Verilog?
Right. So the difference between WR Spice and this, and maybe yeah, okay, I should have repeated the question. So, are we using Verilog? Can it be defined in Verilog? And then what the difference is between this and WR Spice? WR Spice is a time domain simulation. Okay. In time domain simulation, any simulator given ideal zero loss inductors, if you start the simulation from initial condition that is consistent with flux quantization, the simulation as a whole will be consistent with flux quantization. So you can do a time domain simulation in ADS without all this like fancy stuff, just plain circuit simulator. Do the time domain simulation starting from everything quiescent, everything is zero, you'll get the correct result. So that's the difference here. Time domain simulations natively follow the rules of Maxwell equations, which will give you flux quantization if you're starting from something consistent. Frequency domain simulation won't, because they just apply the voltage and find the solution that's consistent with that voltage. Without the constraint of flux quantization, you don't know where you are. The junctions and inductor models you can program in Verilog A. I think that's what ADS actually, what Keysight actually done with their models. How to automate flux quantization in Verilog at the circuit level, that I do not know how to do, because I mean, how do you circuits can be very complicated. Then you have to find some way to find all the loops and maybe apply some constraints. So I don't know how to do that. Maybe it's possible.
Final question: how are these methods comparable to the EM solvers like ANSYS?
So how does these methods comparable to EM solver like ANSYS? So we are not solving for the geometry and the distribution of the fields in a particular piece of metal. We are abstracting metals to lumped circuit elements, even distributed circuit element, doesn't matter. We're abstracting them to symbols in a schematic. So I think this complements EM simulations, and you have to iterate. You have your design in a circuit level, then you try to implement it, as Eli said this morning, as layout. You simulate the layout in ANSYS HFSS. You get values that you can plug back into your simulation. You get parasitics, and you can see if this thing still works.
Okay.
We have one last question in the back.
But this might work in a fully model. Do you imagine it would work at least defined with like lump boundaries that you can place into a full wave model with sort of model?
Yeah, sure. So you can take the junction model, for example, with its flux quantization and everything, and stick it on ports that you got in HFSS and run the simulation in whatever engine you have. So I think that should work fine. Yeah. All right.
Okay.
Thank you very much.